Hello, this is day one from chapter 11B, so this is the second half of this unit, and it is related. Well, it may not seem like it at first, but we definitely still have this chart, the powers you need to become friends with. Don't go logging without them. Haha. We can use logs very usefully when we're dealing with exponents, ultimately. But before we get into it, let's just see what this could be. Let's use some logic here. 10 to some power is 85. We know 10 to the first power is 10, and 10 to the second power is 100. Therefore, reasonably, we could assume that this exponent has to be between 1 and 2. So we want to get 85. Let's try it out. 10 to the, I don't know, let's say 1.5 power. And we get 31. No, we want 85. So let's try 1 point. Well, we can't go 2, so it's got to be 1 point something. 6. Nope. 1.7. Closer. 1.8. Closer. 1.9. Closer. But we can't go to 2 because that's 100. So let's try adding some additional decimals to get it a little closer. 1.93. Ooh, that's close. 1.92. Not quite. 1.925. Close, but I think 3. 1.93 works probably the best. So 1.93 is what we get when we're just guessing and checking. Obviously, there's a better way. In come logarithms to the rescue. Okay. We want to be able to write a logarithmic expression from this exponential expression. Right here is the exponential expression. It says 10 to the x power equals 85. We can write that as log base 10 of 85 equals x, just as the sentence below it explains. Now this is a little weird looking. We have seen this before perhaps, but log always has to have a base. If it doesn't have a base, it is automatically base 10. That's a little coincidental because it's only for base 10 and we happen to have base 10. So calculators automatically use base 10. So in this case, I could technically write it as log 85, no base. That's fine. Calculators will interpret this correctly. In graphing calculators, there is an option to insert a different base than 10, but most scientific calculators are just base 10 and that's it. So both of these are equivalent expressions, and this is the only time you can write log without a base, when it's base 10. So just so that's clear, if this was base 8, then we would have to write log base 8. However, so this is the way it's set up. You write the word log, and then it has what's called a subscript. So it's like the opposite of an exponent, where the exponent hangs up here a little higher. This subscript hangs a little lower than the rest of the characters. So log base 10, and then regular number position 85 equals x. So instead of, in this situation, we have 10 to the x equals 85. Well, x isn't by itself. We have to solve for it. If you write this as a logarithm, x is solved for. A logarithm is always equal to an exponent, essentially. And we can do this, log 85. Let's check it out. Log 85. Well, I wrote og. And it went base. So they want us to have a base 10, or log 85. There we go. They say it's 1.929. We had 1.93, pretty close. 1.929. Nice. So again, just type in log. If you type in log and they want you to have a base, this one doesn't, but then you would type log base 10. But it was fine without it. So really, we just need to become familiar with this and be able to translate back and forth. Another excellent math teacher I know just calls this the whoosh method. So if you take the base, these are logarithms, right? It's a logarithmic equation. We want to change it into exponential form, the one that we know better. So we just start with the base, log base 27. So base, we start here, and we kind of make that like Nike swoosh symbol, but instead we say whoosh for no apparent reason, but it works. I just grab the other side equal sign and then come back to the number. So whoosh, and you get 27 to the 1/3 power is 3. Then we could check and see if that's a correct equivalency, you know, the third to the 1/3 power is the third root of 27. Yeah, that is 3. But that's not the point. The point is to just rewrite this in exponential form. So we're actually not doing any real math. We're just rewriting it into a different way of expressing the same situation. Log base 16 of 4 is equal to 1/2, or whoosh, it's 16 to the 1/2 power equals 4. All right. We should go backwards now. We have it written as an exponent. We want to write it as a logarithm. This is where it's maybe a little bit more challenging because we have to start writing the logarithms now, and we just saw them for the first time. But fortunately, all we got to do is write the word log and go whoosh again. That's how that works, and it's nice. So in the order in which I took these numbers, started at the 2, I hit the 1024, and then ended up at 10. So we write them in order. Log, the first number is the base, so 2 base 2 of 1024 is 10. And this works out because remember I said a logarithm is always equal to an exponent. And there's the exponent, and there's the exponent. So this is a log expression. We did it correctly, and we still whooshed it. Same thing here. We'll write log base 2 of 1/8 is equal to -3. Log base 2 1/8 is equal to -3. And as you can see, it's just the same direction of this little whoosh arrow that goes in the same order, and it tells us what to put where, just left to right. All we had to do is write the word log. Evaluate each expression. So I'm going to take a little tangent here just for a second. This expression, it looks like it's missing something. It's missing the thing we don't know. And this may look a little weird, like, wait a minute, why do we have to add an equals x here? Okay, that's a good point. But recall when we had like something like 3 squared back in the day when this was like fresh. We had 3 squared, and we just evaluated this. We said, oh, 3 squared, that's 3 times 3, and we get 9. We didn't have to go, okay, 3 squared equals x, and then start thinking it through. We didn't have to do that because we learned this first, and we conditioned ourselves to know that this is just evaluating a number. This logarithm is the same thing. It's just that we have to retrain our way of thinking so that we can view it in terms of a log and naturally know that it's looking for an exponent. It says the base to some exponent is 125. Or you can just write it equals x and go whoosh and say this is 5 to the x equals 125. Now it's a little bit more clear what we're looking for. 5 to some power is 125. It'd have to be, you could check your chart, but it'd have to be the third power. So x is 3. But again, back in the day when we were just doing exponents, we didn't have this negative x or this equals x thing here. We just said, 3 squared, bam, it's 9. So same thing here. We could just forego all this stuff if you really got skills and just say, log base 5 125 3. Same thing. These get a little bit more challenging. I'm gonna write x because I want a crutch. Just it's easier to visualize, basically. Now I can whoosh it. Let's see what we're working with. 5 to the x is 1/625. Now, one good way that I've found to do these, just to explain it really, is if you have some equation like this, and it's possible to write any of the numbers in terms of some base and an exponent, like I could rewrite it as a number to a power. I should go ahead and do that just to see if I can make anything jump out at me. 5, it has an exponent x. There's nothing I can do there. 1, nothing I can do there. 625, I can write that as a number to a power. That would be the same as 625 is 5 to the 4th power. So if I rewrite this, maybe I'll start clicking. 5 to the x equals 1/5 to the 4th. So I didn't really do anything. All I said was, 625 is the same as 5 to the 4th. Maybe if I write it this way, something will jump out. Well, kinda. The only thing that's keeping these two sides of the equal sign from looking the same is that we have 5 to the 4th on the bottom of a fraction. We can actually use a property, an exponent property, backwards to make this work for us. I don't want this thing to be on the bottom. Like, this thing's not on the bottom of a fraction. The left side is not on the bottom of a fraction, so I don't want the right side to have, the 5 to be on the bottom. I can move it, and I'm not cheating as long as if I move it, I change the sign of the exponent. Remember when we had a negative exponent on top, we had to move it to the bottom and then make it positive? Same thing here. We have a positive exponent, and I just want it to be on the top so each side looks the same. I typically don't want negative exponents, but I want these sides to look the same. So when I do that, I'm going to have 5 to the x equals, this denominator is now up on top, and it's 5 to the negative 4. Now it should really jump out at you. We have an equal sign. That means the left side is equal to the right side. We have 5 equals 5. They both have exponents, x and negative 4. 5 to the x equals 5 to the negative 4. X has got to be negative 4. Everything else is equal. And we have an equal sign. So therefore, we can evaluate this as negative 4. Now that was a longer process than we probably wanted, but it is one of the better ways that I've thought of to just make this more manageable. And when you look at this, we don't really know what to do. So if at any point you don't, try and see if you can change any numbers into a number to a power. We'll use that same method right here. You should, probably pause it and give it a shot, but I'll start working through it because you can pause whenever you want. I want to write this as an exponent to see what I'm working with. So I'm going to say equals x and then whoosh it. 9 to the x is equal to 27. Now, fortunately for us, we're really good at exponents and knowing numbers to powers. And 9 itself, it's raised to an x, but 9 could be written as a number to a power itself. It's 3 squared. So 3 squared, but that's also being raised to the x power. Yikes, that's ugly. And 27 could also be written as something. It's 3 to the third power. So one nice thing about this is by doing that one thing, just seeing if we can rewrite any of these numbers as a number to a power, we ended up with two numbers with the same base. We still have a hiccup in that this left side, we have a power to a power. Hopefully by me saying power to a power, it just retrieved some memory for us that there's a property for that, an exponent property. Power to a power, multiply the exponents. So this is 3 to the 2x power equals 3 to the third. And now this is kind of a funny step in math where some of this equation is irrelevant. 3 to the 2x equals 3 to the 3. Well, I just want to find out x. And the bases are the same, so they're equal. Therefore, the exponents have to be equal. So I'm just going to take this off to the side and say, well, exponents are equal. 2x equals 3. Now this is the equation I want to solve for x. I kind of don't care that they were both base 3. They just had to be for me to say that these are equivalent, which they are now. You solve for 2, or solve for x by dividing by 2. So x is equal to 3 halves, or 1.5. Neato. So it is kind of cool that we creatively use some of these properties just to make things look the same. We substituted them in because they are equivalent, and then we made them look nicer for our memory to adjust to see that this is like, oh, we have equivalencies here. So this is the first day of logarithms, and hopefully this makes sense. Good luck.